Good morning everyone. So a little bit of JJK to get us in the mood for some maths. So today what we're going to be looking at is a bit more probability, and we're going to be looking at how things are distributed and some of the different little bits of language we have with it. But we're going to be looking mainly at binomial distribution, which was something you did with Mr. Cooper in the first lockdown. So depending on how much of that you did, you will need to pay even more attention than you would do otherwise. But it's actually not tricky, and it's one of those things which the calculator can really help us out on, in a way that in the past you had to do lots of stuff with tables and work all sorts of other things out. There are easy marks here, folks, so you really want to pay attention, do some practice on this, and it will pay you back double. So how to start this off, right? If we've got a normal dice, so if I roll a fair dice 1,000 times, how might I describe the distribution? Well, what are the possible things that can happen? So we could put it down in a table as to what we score, having rolled each one if we counted. And there would only be 6 things that can happen. So is this going to be, what sort of data is this going to give us if only 6 things can happen? Would it be continuous or would it be discrete? And that's really the nub of that question there. That distribution is going to be discrete. It would also be random, wouldn't it? But what would happen? What would you say if I got 300 6s? There would be another 700 rolls, wouldn't there? If I divide 700 by 5, and let's just pretend that all the other numbers came up exactly 140 times, would you start to question my original statement that I've got a fair dice? I think you would. Now, if you had different numbers and you were interested in other things other than the 6, you wouldn't be able to do it with what we're going to be doing, which is a binomial distribution. But if you're only concerned about whether it's a 6 or not a 6, all of a sudden, instead of saying we've got 6 events that can have 6 outcomes, we could say we've only got 2, whether it's a 6 or whether it's not a 6. And that's what we're going to be looking at now with this next problem. So let's look at this biased dice of ours that's got a probability of landing on a 6 of being 0.3. Hannah rolls it 15 times. We're now talking, it says state any assumptions that are required to model the number of 6s as a binomial distribution. State the distribution. So pause the video, have a go, see how much of this you can do. Some of you will be able to do this maybe without any further help, others not so. Right, so the assumptions that you make are, there's a few of them. So the first thing is that there are only 2 things that can happen. We don't normally use the word things, we normally say it can only take 2 values. So it can only take 2 values, 6 or not. So that's the first one. The next one is the probability is the same every trial. Now there are 2 marks, so I reckon you're going to need at least 2, quite possibly 3. And the next one is that, and this one's absolutely right, there are a set number of trials. So there are a set number of trials. So Hannah's done this 15 times. If we didn't know how many times she did it, we wouldn't be able to make predictions about how many times she'll get a 6. And the last one is very, very similar to the probability is the same every trial. It's that each trial is independent, and I don't really see how they could be the same every time if they weren't, but each trial is independent of the one before or anything like that. So those 4 things we need to have in there. Sorry about my writing, there's a bit but I wanted to put all that. So actually that's 1 mark, isn't it? Because it then says state the distribution. So the distribution is binomial, and they've told us that. But what does that look like? Now we normally use a capital letter, and if we're just doing 1, we normally call it X. You can have a Y or whatever. And that we are going to model as a binomial distribution. So we show it's binomial by putting a B outside the bracket. Then the first thing we need to put down is how many trials there are going to be, and then the probability. If you get it the wrong way round, you lose the mark. So that is number of trials, and there's our probability. Right, now when it comes to finding the probability that Hannah rolls exactly 4 6s, it's a good idea to do a little sketch beforehand so that you can think about what's going on. And when we do, we can also think about how many times we expect to get a 6. So if you were to get your calculator and just do the number of trials times the probability it happens, the mean, the expected mean, would be 4.5. So I'm going to use that to help me just make a nice little sketch. 0 up to 15, because that's the most number we could have. The most likely number would be 4.5, although that's actually impossible, isn't it? Because this is a discrete one. So actually we would have 2 things. We would have the probability of a 4 and the probability of a 5 as a discrete sort of bar either side of that, both of them being a little bit less likely. But anyway, we want exactly 4 6s, so ignore that bit. We just want that probability there. And in order to do that, we need our good old friend, the calculator. And you're not going to need any more working here, just the answer once you've done this. So the first thing is we want menu and statistics, so menu 2. Then we want distribution, so that's F5. Binomial, that's F5. So all flagged quite nicely. This is cumulative. This is just on, so we just always go with this cumulative. You can set it whatever you want. You could do it on the other one, but here all it means, because we only want 4, we set our lower as 4 and our higher as 4. The number of trials is 15. The probability is 0.3. Press execute one more time and we get 0.2186. So the probability that x equals 4 is 0.219 to 3 significant figures. So these do need to be kept as that. If you were using the tables, which you're allowed to, you would get a 4 decimal place figure, but you would still need to round that. Now next one, finding the probability of 2 or fewer 6s. So 2 or fewer is going to be, if there's where 2 is, we are looking at the probability of that. There's actually 3 results you could have, isn't there? There's 0, 1 and 2, and what the calculator is going to do is add those 3 together. So we're looking at the probability that x is smaller than or equal to 2. And if it had just said fewer than 2 6s, we would have actually have gone for 1 or less when it gets into the calculator, wouldn't we? Right, so back we go. We want the lower as 0, the upper as 2. Trials and probability stays the same, 0.1268, so to 3 significant figures, 127. Okay, now throw this one in there. It's actually going back to earlier on. Pause the video, have a look, and write down what you think for each of these. Right then, so if something's discrete, it can only take certain values, and if something is a random, then it can take any of those ones, and we've got no control over what it's going to be, is it? So that's what we've got to think about. So a seed chosen randomly from a group of plants, it is random, but the height of a seedling is continuous. So not discrete because the height is continuous. So anything that you can measure rather than count is generally going to be continuous and therefore not discrete. The second one, a dice rolled, a fair dice, so because it's fair we can say yes, it's random, and because a dice has a set number of things it can land on, it is discrete. So yes, it's yes, because what I just said, because there are a limited number of distinct results possible, in this case 6, it doesn't matter how many, and it's random because of what we said. Yeah, random because there's no way of saying which one it's going to come on. It's going to come up equally for each one. We do not know. The last one, it's discrete, but it's not random, as there are always 7 days in a week. Okay, so it's just the dice. So that's what we're looking for. Hopefully that might clear up one or two things that you might not have thought about there. It's very easy with probability to assume that everything is obvious. It's not. So if there is anything that is troubling you over this, please do let me know. Right, we're going to have a go at one more question here right now. So the probability of a switch being faulty is 0.08. A random sample of 10 switches is taken. Pause the video, have a go, see how far you get. Right, so your suitable distribution model would be a binomial. So we can call that B, and then our probability being our number of 10 switches. So that's our number of trials. Our probability is 0.08. So that'll get us 1 mark. Justifying the choice, you can say because there are a set number of trials. That's the first thing. The probability stays the same every trial. Trials are independent, and And lastly, it's called binomial because there are only two things that can happen, just as in binary you just have zeros and ones. There are only two values the trial can give, faulty or not. Okay, so that's part A. Part B, finding the probability the sample contains 4 faulty switches. So 10 times 0. You would expect on average to have 0.8 is your expected mean. So we're looking for exactly 4 faulty switches. And that means, if I get this bit ready, okay, probability x equals 4. Then if I get a calculator and go back to where we were, lower is 4, upper is 4, number of trials is 10, and probability is 0.08. And that's giving us that. So that is 0.005, isn't it? 1, 2, 3, yeah. 2, 2 to 3 significant figures. Right, and now the last thing to say is, in order to get a bit of practice on that, I'd like you to have a go at the Maths Genie sheet that I put on, which is all to do with discrete random variables. There's 4 questions there. I haven't gone over everything that you would find on there, but there are worked answers attached as well. So have a go at it, then see how you got on compared with that. And having done that, if you're still confused, please let me know. All right, enjoy, folks.